I think this is a waveguide problem, right?
It is, yeah.
And I forgot to link to the guide. You have a source, right? I'll just put this in and we'll fill in the values in a second. Then you had some source resistance. Then you have a waveguide. And then you have a load here. And the waveguide has a length L, I don't remember what it is.
0.482 meters.
0.482 meters. And then cross section of the guide.
A is 22.86 millimeters.
And B, so A is 22 millimeters, right?
22.86.
6 millimeters, and B is
10.16 millimeters.
alright. And let's see. I know the first thing we have to get is the characteristic impedance of the guide, right? And to do that with the operation frequency, first BS is at 50 volts. I honestly forgot.
It's 10.
10 volts. And F
is 8.2 gigahertz.
8.2 gig. And so now we find the frequencies first for the cutoff frequency. Is it air filled?
It is, yeah.
All right, cutoff frequencies. C, because I'm using C because it's air. Otherwise, I put 1 over the square root of mu epsilon here, divided by 2, and that's square root of m over a squared plus b over c squared. Now this is straightforward here. The only thing you need to do is make sure you have a square root operator and you're squaring things inside there. So you look at the FC10, right? And that really is just going to be c over 2a, right? And 3 times 10 to the, can somebody just give it, please?
Yeah. It's 6.5 gigahertz.
6.5 gigahertz. Next one is going to be double that. FC20 is going to be double that, or 13 gigahertz, right? Wow.
Yes, sir.
13 gigahertz. And then the next mode is FC11. And that's going to be what, 15, 16, something? I can't tell. It's M and N equal 1. We're slightly higher. What is it?
14.8.
Is that it? That sounds about right. 14.8 gigahertz. All right, so these are the first 3 lowest order modes, in case you're asked that, right? The lowest frequencies of propagate. Now, I want to make note of this. This can only be a TE mode. All right, the 1.0 is only TE, no TM. Follow me on that, class? Everybody? Now, this mode, the 2.0, is only TE. So you should put a TE to a TE 1.0. Follow me? Now this could be TE or TM. Both modes will be excited if the frequency of operation is greater than 14.8 gigahertz. Follow me on that? But these can only be TE. Now we look at the operating frequency, it's 8 gigahertz. This mode will propagate, it'll be developed. This will not, it's too high frequency. So there's only one mode of operation, as it should be. Everybody got that? All right. Now, after that, next thing we have to get is the characteristic impedance of the guide.
Dr. Baginski, wouldn't the second mode be like 0, 1 for the TE instead of 1 or 2?
Well, let's try it. Maybe you're right. Let's see. FC01. That would be C over 2B. So tell me what that is. I can't. Maybe you're right.
That should be 14.76. I don't think FC1 was.
The other one was 16.
What is this? The 01? Can you just tell me?
I have 14.76.
What is it? I'm asking. You're asking. I'm so glad I'm so captain. I think my thumbs have gotten fat over the years.
C over 2B?
Yeah. Anyway. Go ahead, what did you get?
I think it was 14.
No, you punch it now. I wonder if it's just. B is.
Yeah, it's 14.7.
Yeah.
14.76, right? 0.76. All right, so this is actually the mode that comes before this. They're close, but I guess the lowest order modes would be technically this, this, and this. All right. Actually, how come? is more than twice B. Did I do something wrong? No. 14.76, is that 14.8 on the nose? I think I put these down, didn't I put a whole bunch of them, all the frequencies?
You put 1020 and 01.
All right, well, if I didn't put the 1020 and 01, so that was, I guess you were right, my bad. The 11's usually the lower, is usually lower than, or sorry, 01, 11, yeah, all right. It can be close, and they are very close. Anyway, those are the lowest order modes, okay? Now, we know there's only one mode that's gonna propagate. Do y'all agree with this? And that's the TE10 mode. So now I've gotta get the characteristic impedance. Thank you for letting me know, Bobby, to always check the 10 mode. For the characteristic impedance for the TE, and this is the 10 mode, that's gonna be simply the characteristic impedance, and it's really beta naught here, over K, and K is equal to the square root of 1 minus, and here it's gonna be the cutoff frequency, which is, for the 10 mode, 6.5 gigahertz, right? And it's over the operation frequency, which is 8.2, and you have to square that. So can you give me the value of K?
610.
By the way, did these numbers square with, I mean, the numbers we're getting now square with what was on the solutions? Okay, because I do that with MathCAD, I've never had a problem with inaccuracy there, as long as I type the right values in there. All right, 0.610. Now this, beta naught, is just 120 pi, 125, so what is the characteristic impedance for the TE mode? I'll just call it Z naught from here on. It's 120 by 377 over 0.61.
628.
628?
Yeah.
You getting that? 628 ohms, okay.
I redid the 1 mode, and I think it's 16.15.
For the 1-1?
Yes, sir.
Okay. 16.15 gigahertz, which means this is, the modes would be this, and then this. All right, yep.
So, like on a test, should you do all 4 of those modes?
Normally,
and then-
you can check them and just pick the lowest 3.
Okay.
But if it's a double mode like this, some people will say, well, that's 2 modes there. Yeah, it is. But just, you know, the lowest, say, 3 frequencies of propagation would be this, and this for that one. It would be the 01 mode, okay?
But it could change per problem.
Well, the dimensions of the guide, we can talk about this in a bit, but if I make the dimensions of the guide where this, A is not greater than 2B, then you can get some weird stuff, but I'm not trying to deceive you with these things. I'm just trying to give you, that's a standard guide in terms of its proportions. All right, that's standard. Just, you know, check the lowest, if you go 01, 02, 10, 20, 01, and 11. Those are the lowest possible frequencies, mathematically, they can propagate. You can put them in the order they appear. It'll always be the 10 mode is the lowest. All right, now, once we have that, what we have to do, because I know where we're going with this, we want the voltage at the load, we want the reflection coefficient, we want all the standard stuff, and now we're gonna start looking at this thing like a transmission line, not a actual waveguide. So the next thing we need is beta in the guide, right? Beta in the guide, and that's beta unguided, right, times K. So beta unguided is, well, it's really what? It's technically omega times square root of mu over epsilon times K. Omega is 2 pi F, right? And square root of mu epsilon is over C. Y'all follow me the way I'm doing this, class? I'm just showing you that this is technically omega square root of mu epsilon is beta for a lossless medium. It's the unguided beta. Now we have to multiply this by K. And straightforward 2 pi times 8.2 times 10 to the 9th over 3 times 10 to the 8th times that value of K. And can somebody give that to me?
It's 104.76.
All right, now everybody check yourself. Make sure you get this. This shouldn't be a difficult calculation. 104.76. And that would be radians per meter, would be the units of this, right? Then after that, now I go to the equation where the most errors are made. If you don't mind, I'm gonna erase this middle board right there, the middle part. I was coming in this morning, so I left, I thought, with plenty of time. And I don't know, if parents don't like to let their kids walk to school when it rains, but coming down Sanford, took 15 minutes, I think, to get through there and through the turn, or not Sanford, from Mooresville Road to the turn on Sanford. I couldn't believe that. It must be when it rains, the parents will not let their kids go to the bus stand and wait or something. All right, now we go to this. Zn. You have to get the input, the characteristic, or the input impedance. So the first thing you have to do is, and I'll give you this calculation, I'll give you this on the quiz. Hint, you don't have to memorize this one, but if you use it enough, you don't need to worry about it. Times ZL, right? Plus, then it's J Z naught, and that's Z naught for the TE mode, 1 mode, times the tangent, and you have to be sure this is beta in the guide times L over Z naught plus J ZL tangent of beta in the guide times L. And for ZL, it's shown there, but what was L?
100 ohms.
So ZL is just 100, and that means you got Z naught there, I forgot what it was, ZL is 100.
628.
Z naught is 628 ohms?
Yes, sir.
Okay, now you got beta, beta is 104.7, L itself is 0.482, right? And that's meters, so you've got to do the product, and what's smart to do is this, take beta in the guide times L, and get that right out of the way, because you're gonna be putting that in twice. I just wanna make sure we're consistent, that everybody sees this. It probably wouldn't be a bad idea to take the tangent of beta guide times L and put it in the memory, so you can just pull it back, but, anybody on that? 50.49. Remember, this is radians, not degrees, so when you do the tangent calculation, do the tangent calculations in the radian mode. Got me on that? But that's a mistake people will make. It's very easy, especially at 8 a.m., to not remember that the mode is critical there. You just put the order. All right, now after that, now you just turn the crank on this, right? And if you could, after you turn the crank, you can compare it to the answers I gave you. Give me both the real and imaginary part and magnitude and angle for this. Now, I gave you the answer to this, and you said you had trouble getting that answer, or was it something else?
Yeah, for some reason when I put,
Just, how many got the answer I gave you? You got it? Anybody else? You got it? Got it? All right. I'm gonna say this. Be careful with that, what I told you with that radian operation. The tangent operation has got to be done in radians. If it's not, the whole thing falls apart. But I want the magnitude and angle that you guys get on your calculator. If you got your calculator, give it a shot to do it. Go ahead.
456 and an angle of -70.9.
Would it be, can you give me the real and imaginary? Just the real, I want both for both of you guys, because when you're doing this in your calculators, I want to make sure you check. And all you guys can see.
456 e
456, go.
e to the -1.238.
No, that's I want real would be 456 plus J something. I want real and imaginary polar. I don't want polar, I want rectangular, sorry. Get it? I mean, can you give me right here? The real and imaginary that?
148 minus J431.
Wait, 148? Is that right? Minus J what?
J431.
That sounds right, 431. Can anybody else else confirm or deny? Check your calculator, this is the most common error, I promise you. And in this particular problem, this is a decent amount of points, right? So you gotta make sure you know how to do this in your calculus. And I know so many people are very casual about it. They think, oh, I got this, and then they don't got it. You write the right equation, the wrong answer comes up magically.
I'm still not getting it. Even with all of our answers.
Tell me, what do you get for the tangent? Just, could you give me just the tangent of beta? Because this is where probably the error is.
Tangent of beta L.
Beta guy times L. What do you guys get for that? Numerically.
2, 3, 2, 9.
All right, what'd you say? What'd you say the answer you got for the tangent?
2, 3, 2, 9.
All right, check that. Anybody?
176.
Yeah, that sounds more exact. 0.176? Anybody else get 0.176 for the tangent of beta G times L? The tangent of 50.49 radians. Make sure it's in radians.
Yeah. So you have me 0.228 in radians.
No. The answer is just real. The angle, this is in radians. So the tangent of something is 50.49, where you're doing the tangent in radians. You said 0.1 something?
0.176.
I'm getting 0.2284.
For that value, same value, there's a problem. This is, now at least I identified inconsistency. Can you guys figure out where what are you getting? Just use 50.49, don't,
Okay, sorry.
could be a rounding error. What do you get?
0.2284.
All right, 0.2284. All right, now if you just stick this in where the tangent beta G times L is, and then do that calculation, see if you, I wanna make sure everybody can get this number.
Just the J, say the not.
No, I want either one, either this or this, but you should get magnitude and angle. Is really the one thing I want.
The values that we have, I'm getting 174.7 and 8.53.
Are you getting this number though? or no? All right, give me both numbers, because now, what did I put in the in the solutions? I know those are right.
I'm getting the same thing he is, 177 at an angle of 53.3.
Guys, does anybody have access to solutions? I can pull them out, but.
I've got them here. The solutions say that the answer is supposed to be, where is it? It's
457 at an angle of negative 70.9 degrees.
Yeah, correct.
With those values?
Yeah.
They're close, it's just little rounding things that.
All right, what did you get?
105.076 plus J.
All right, how about, give me a magnitude there.
174.717 at an angle of 53.03.
And is that close to the answer on the?
I got that just now, but I got the right answer yesterday, so I don't see what's happening.
I got it. Now you got me what? I know this equation is always the one that causes everybody to mess up. And usually it's the tangent value. That's usually the case.
But that's nowhere near the. I got some more.
Yeah.
Just
Yeah,
small-
yeah.
That's not just rounding
Like,
error.
to the T.
It's only the small rounding error.
Yeah, I'm still shooting, but I have no calculator.
Oh,
What did you say? What?
we are using a different beta G than in the homework. It's
Yeah,
like one of the
beta
three
G
in the
was
homework.
103.
Wait a second, is the homework, is there,
Yeah. There's just one or two different.
all right, here, you can help me out here. First of all, in the homework, is RS, is the source resistance 100 ohm?
Yes.
Is the dimension 0.25?
Ours is 200. Our L is 100.
All right,
Well, that hasn't affected us
Is
yet.
that it?
all right, here, hold on. I mean,
Reading it.
8.2 gigahertz, right? And A is,
A is 22.86 millimeters.
B is,
10.16 millimeters. And the length is 0.482.
and what's RS?
200.
And, operational frequency. So then. Let's see, 10. FC 106.562 times 10 to the 9 is right. VS is 10 volts, is that right?
That's correct.
And ZL is what?
ZL is 100.
All right. And so we got, xenon is 628.6. Okay. So then beta, unguided is 171.74, beta guided is 102, my 0.997. Is that what you guys are good? Okay, we're good there. All right, now L on this one is 0.482, is that right?
Yes. 4.82.
0.482?
Yeah,
Is that correct? Okay, so when I do this, and I get ZN, I got 457.543 at an angle. Well, I got 149.204 minus J 432.532. Is that what you guys get?
I got that one last night.
How many got that? All right, I mean, how many got a magnitude of 457.532? Did you not get that?
Well, I was just plugging in the numbers that we found, but I think the difference is the beta G that we found and the Z naught.
The beta G is 102.997. I mean, right here, that's the right value.
Yeah.
What do we have up there?
We got 104.76.
All right, somehow we got a rounding error there.
And I think it comes from K.
Okay. So what was K? K is 0.061, but it's rounded here. Okay. Is that what you got? Problem is, see, this thing, I want a more exact answer. I have to go to math formatting.
That's 37.6, but if you're getting more exact.
I got 0.6.
Yeah.
Is that right?
Yes, if you do 6.56 on the top. It's
Yeah.
6.5.
That's it. Okay, so these are small little things that come out to mean a lot in air. All right, is that the right value here then? Now everything changes, right? Do it this way. I'm gonna assume if we get this value of K right, and that value of beta, and it's 102 point something, I forgot exactly, 102.1?
You said 102.9.
If we get this beta guy, if that's right, and the value of Z naught is correct from using the value of K, then this equation should work. And what I get for the answer for that equation, if you check it, I'm getting ZN's got a magnitude of 457.543. And I don't have the angle here. Can somebody give me that angle?
Negative 70.9.
Can you check that, guys?
I just did that with the new beta, with beta of, what did you say, 102.997,
Yeah.
and that worked.
Okay, is that the angle?
It's really close. I think it's the exact same thing.
All right, well, there's gonna be some round off here. The reason there's such a huge change with such small, there's small changes is because the number, the wavelengths per meter on this, radians per meter. 102.9 radians per meter is an enormous amount of phase change. Phenomenal. So very small differences in length or L times beta G will cause large differences in the value of the tangent function. Remember that. Okay, if that's right, assuming it's right, then the next thing you need, by the way, does this check with you? Because you're the one that brought this up. I bet you anything, if you got the right mode for the tangent, you're getting something a little different, probably has to do with roundoff error. I'm gonna bet. What did you get?
505 at an angle of negative 1.737.
Degrees or radians?
And it's calculated in radians.
What calculator?
HP prime.
HP prime? Oh man. Anybody else here use HP? You're the only student I've seen in a long time that uses HP. I have, that's calculators I know. All right, well.
If you're in radians, are you sure that angle is in degrees? Because the angle here in radians is minus 1.24 for me. Like it's close to what you said, I think. If that's in radians. That would get you
Well-
closer, that's still not there.
Here's what I'm gonna say, if you're getting a different number for the magnitude, if you're getting the same values for Z naught and ZL, if you agree there, and you get the same values for the tangent, it's gotta be right here. The tangent of beta G times L has gotta be the thing that's causing the problem. That's where the change occurs so fast. And I'm just betting that's the problem. Now, sometimes when you take a real and imaginary number, divide by real and imaginary, your calculator's getting a little confused at times, so you've got to take care about that. What I'd recommend is do this calculation first, store it. Do this calculation, store it, then do the division. I'm just telling you, these are the typical kind of problems you run into. Did you still have?
I'm still getting that 505, but the angle's right if you convert it to degrees.
I got the answers here. I'm running the calculations, and that answer's right for 457.
What do you get for that tangent? For a tangent, 1.997
Engines 102.997.
times 0.482. Minus, yeah, 0.71, yeah. He's getting the same thing for tangent.
If you're getting the same thing there, then the division,
Maybe the way you're calculating complex numbers, that for calculator is not wrong.
what's that?
Maybe it's the way it's calculating complex numbers, because mine was sometimes off with complex numbers. But it's because it's very finicky about how you function.
Now, he has an HP, so you can store, like, you can do the upper calculation, store it, then do the lower calculation, store it, and then recall the upper divided by the lower. I think you can do that fairly easily. Look at it, eyes. Did you get this too? Yes?
Oh, yeah.
You got it?
We're good.
Tina, are you sure that Xenon that you've got is 628?
Yeah, it is.
I'm gonna say that these things, when you have a large value of beta, you gotta be very careful, because small changes have large variations in Zn. All right, if that is the value, then the next thing we have to do is get right on the inside here, we gotta get what I call either V prime, or you gotta indicate Vn, something like that. And V prime here is just gonna be Vs times Zn over Zn plus, in this case, Rs, and Rs was unstated. What was Rs for the problem? Well, I didn't write it down. So 100, 200?
RS is 200.
The 200 guys? All right, 200. So, plus Rs, and you're gonna get a value here. Now, I don't know what that value is, but you can give that, I'll be right there. But that value, not the end of it, that value is actually equal to V naught plus, which we are after, times e to the j beta in the guide times L plus the reflection coefficient at the load times e to the minus j beta in the guide times L. Now we're gonna go get V0 plus, but I gotta also get the reflection coefficient because I'm spending a lot of time on this. The reflection coefficient is gonna be ZL minus Z naught in the guide over ZL plus Z naught in the guide. So this is gonna be, the load is 100 minus 628 over 100 plus 628. And you can give me that, it's got a negative on it. So first give me this one.
So I got 8.23 at an angle of negative 19.88 for a fleet run.
At an angle of 19 point
Negative 19.88.
degrees.
Yes, sir.
All right. So now we've got that, and give me the reflection coefficient. I think I've got this right here. Reflection coefficient for, I don't have that right here.
Should be negative 0.726.
Minus 0.726 is what I got. Point. All right. Now, we have to calculate G0 plus. We're almost there. And that's gonna be equal to 8.23 at an angle of minus 19.88 divided by e to the j, and it's beta guide, or beta g times L, whatever that is, plus the reflection coefficient, which is over there, times e to the minus j beta g times L. And give me that too in terms of the magnitude and angle, if you don't mind. I have to use a FlexLM license. First, I have to start something called Global Protect. It's a VPN connection. Then I have to activate the license on here. It's about a 5-minute process. It's irritating. All right. I can do some calculations, but I can't get the angle. That's the problem. What did you get for this, V0? Magnitude. For V and G, you get 8.23? Yeah, that's right for V and. And so for V naught, the magnitude is gonna be 8.005. Now what's the angle, what angle do you get? So it's 8.005. At an angle of 16 for what? Is it 16?
16.3, I think.
Is that, John, 0.3 degrees?
Yeah, 58.73 degrees.
Yeah, I've been.
58?
58.73.
All right. Maybe I'll have to do the global. Anybody?
57.6.
57.6 degrees. I'm gonna go with that one for V0 plus. The next step, they want voltage at the load, but we're really at this point, the problem basically is done as far as the difficult calculations. Now to get voltage at the load, I'll put it over here. The only thing, we know voltage in general on this transmission line is some V0 plus, which we have just calculated, it's times e to the minus j beta in the guide times z, plus reflection coefficient times e to the plus j beta in the guide times z. Now, because this point, and the notation Whitworth uses, this is at z equals 0. All these values are negative z, and this particular point is z equals minus L. Now we want the value of the voltage at z equals 0 at the load. Y'all hear me on this one, guys? This is important. So to get the voltage at the load, the only thing we do here, we say voltage at the load is simply V for z equals 0, and that's just V0 plus, which we calculated times 1 plus the reflection coefficient at the load. Y'all follow me? Now the reflection coefficient is strict real for this problem, and it's minus 0.726. So take 1 minus 0.726 times V naught, and that is the voltage at the load. Can we give that?
2.19 at an angle of 57.6.
2.19?
Yes.
57.6 degrees. Okay, that's the voltage at the load. If I asked for the current at the load, how would you get it? I think I did, but I don't remember.
Divided by load resistance.
Just it's strict it's resistance, right? Just divided by the resistance. That's the current at the load. So we want current at the load. We just take voltage at the load divided by R load, whatever that is. And I think it's written down on the problem.
Just 100.
What is it?
It's just 100. The,
100?
the resistance at the load?
No, the current. It's VM over R.
0.0219 at an angle of 57.6.
0.219, sorry, divided by an angle of 57.6 degrees. Now, what's the power at the load? Power dissipated by the load, is the average power. P at the load, you can get it a lot of ways. We had a little discussion last time. You can take 1/2 magnitude of VL, in this case, square it divided by RL, because it's a strict real value. Typically, you take the current squared times the resistance at the load. Matter of fact, let me write that down. It's gonna be 1/2 times the magnitude of, it's gotta be magnitude of the current of the load squared times R of the load. It's the real part of the load, if there's a real and imaginary part. That's the way you get the average power. If there's an inductor there, it dissipates no average power. Well, for this one, that's gonna be simply 1/2 times that current, where did I put it? That current, 0.0219. Square that and multiply it by 100, and lo and behold, you should have the power. Can somebody just give that to me?
0.2 watts.
Is that right,
20 milliwatts.
class? 0.2? Just make sure.
0.02.
0.02 watts. Anybody else confirm? You getting it, guys? All right, what else did they ask for?
That's all.
All right, one last thing. If I wanted velocity in the guide, if I wanted, say, the phase velocity in the guide, how do you get it? Phase velocity. Well, it's always the velocity in free space, which would be c, but phase velocity is faster than light, so you divide by k, right? If I want the velocity of energy propagation, what would it be? Or group velocity?
C times K.
C times k, less than the speed of light, almost, or equal, right? Remember that. Okay, that's about, if I wanted the wavelength in the guide, how would I get it? A wavelength in the guide is how the wavelength this way would be 2 pi divided by beta in the guide. Y'all hear me? Follow me on that, guys? So that would be wavelength in the guide. But this, more or less, the reason I do this particular problem, and I really go through it after I give it to you before a quiz, is because there are more mistakes that I see on this problem than all the others in EMAG 2. And they're usually calculator errors with radians, degrees, or something else that I can't tell from just the discussions that you have to figure out in class. All right, that's it. Now, you're gonna get your quiz. I suppose I can do it. I would, because I'm thinking how much calculations, how long these calculations take. I'm gonna go through slab waveguide and then fiber optics on Monday. Now, please be here for this lecture, because the book's treatment of this is a bit confusing. I'm just gonna say slab waveguides. I'm gonna give you a link to take a look at some reading materials. Has anybody ever had slab waveguides or waveguides in physics there? What it amounts to is this. When you have a slab of dielectric material that has, assume no loss, but it's got an epsilon relative greater than the media around it. So it might have an epsilon relative of 2 or 3, and then say an epsilon relative of 1. What happens is the waves ricochet back and forth, just like they do in a perfect conducting rectangular waveguide. But the problem is this. The wave, there's some of that wave that actually penetrates into the second media, and it decays exponentially. It's called an evanescent portion of the field. It doesn't actually, there's no energy loss. It's just like an inductor where it has energy around it. Same with the fiber optic thing. The thing about fiber optics that they learned about the hard way, when you have a fiber optic cable, there's still a field about that cable. There's still a small field that it's like an inductor's field. It is being created, and it basically collapses on itself, created. There's no energy loss there, but what it allows is people to get near a fiber optic cable, and without cutting it, they can put a sensor there, and they can actually monitor what's being transmitted. Now, it used to be thought that it was impossible. Fiber optics are basically invulnerable to lightning and stuff like this. They're EMC proof, but they can be tapped. And they didn't think that was possible at first. You can actually get a sensor very close to the fiber optic cable, and there'll be some of the field will actually, that's ricocheting around, it causes, it's called an evanescent wave. That evanescent wave can be monitored, and it will tell you what's being sent. You can basically tap it. And that causes immense problems for people in the law. It's really the Department of Justice, because they have the most secure, I don't know if you guys know this, but I always thought the most secure communication links were the military. Department of Justice has fiber optic links that go from here to Washington. All this stuff, they were trying to make it impossible for somebody to basically get into the Department of Justice's information about people. But they found that wasn't true, and so then they had to do a bunch of other stuff. But I got a whole story to tell you about when it comes to really eavesdropping electronically on people. And anybody here in the military, past or present? The military have got guys that are they always find these super smart, technically astute people, and they get them involved with things like Wireshark. You know what Wireshark is? How many use Linux operating systems? How many know what Linux is? All right. Well, Wireshark is something that it was developed, I think, by the military. That or a bunch of hackers did it. And what it allows you to do, if you go to a coffee shop, you can monitor the traffic between other people's machines and the routers. Now, I am not an expert in this, but I have found out about these from military guys. And then in doing so, you go through all these standard permutations, you can crack the actual lead part of that, what do they call that thing? It has to do with the data blocks that are the encoded data blocks, and you can decode this stuff and figure out what in fact is being transmitted. And that's why if you ever go to a public place like Starbucks or something, and you're using either your phone or this, please make sure you use encrypted calculator. If you got anything on your phone or your laptop that has to do with credit card numbers, now I have that, right? Because My wife shops on Amazon. It's in these things. It's in the memory, all right? Anytime I go to these places, I will not get on there without using a VPN client. That encrypts data both ways, and you don't have to use Auburn's VPN. You want a VPN, something where you can pull VPNs anywhere in the world, I give it to you. And that way they can't get your information, because your information, is not, don't assume it's encrypted from here to the Wi-Fi server. If it's not encrypted, they can eavesdrop and they can pull stuff. Anybody ever have your credit card stolen? I mean, your credit card information stolen, let me put it that. Or I have, several times. They didn't get it because they got my card. They got it because they got that number some way, and I know there's skimmers on gas and stuff like this. It didn't happen that way. They got it from, I believe it was a coffee shop when I was traveling. Right? That is irritating to know, because I don't like having to do all the security stuff. All right, why don't you do me this favor? Your row, keep it, the first row right there.